Okay, in this video, we'll talk about systems, isolated systems, and the total linear momentum of a system. So, in this first figure here, we have a system. Now, a system can be a region of space, as shown here, in which case everything inside this region is a system, and then I have the boundary line in red here. Or it could be a collection of particles. Let's just say that I had some particles in here. Let's say we have 3 particles here, and maybe they're moving around a little bit, gas particles or something. And I could say my system consists of just these 3 particles. So if these 3 particles were over here instead, maybe even with a different orientation, then my system would still be just these particles, and maybe they're moving differently now because they collided or something. Then my system would just be these collection of particles. So a system is either a region of space or a single particle or a collection of particles. We could have an infinite number of particles in our system. So there can be forces acting within the system. Let's say these are colliding. This is the reason that these particles here change direction, is because they collided. So maybe we have over here in this figure, we have these particles, and they are colliding. Our system includes just these particles here. So I have this boundary. It could be a region of space or just these particles. If my system is this region of space, anything that happens within this system is what we call an internal force. See, these are internal forces. They might be the particles colliding or something like that. Or even if we just called the system the collection of these 4 particles, then any interactions with those particles, one particle with another one, would be called an internal force because it is acting within the system. There could be external forces acting on it as well. So let's say I have some external force that maybe acts on the boundaries of the system or acts on these particles, and these would be called external forces. So this EXT is for external forces. For an isolated system is one which has no net external force acting on it. So this is supposed to be the sum of all the forces. The sum of the external forces are equal to 0, which actually you see here, the vector sum of these forces may in fact actually be equal to 0. So this system would possibly, depending on the magnitudes and the directions of these forces, this system could be an isolated system. So a system is a collection of particles or space, and an isolated system is one which has no net external force acting on it. So take, for instance, if we have this box. Let's say that this box is our system, and including all the particles within it. Now, any interactions that these particles have with the edge of the box would be internal forces. As they come over here and they collide on the wall and they bounce back over this way, then this is an internal force because it happens within my system. So this is internal. If I were to come along, actually if we consider this box to be in free fall, then there's a weight acting down on it, right? And now there is an outside force, the force of gravity, which is acting on the box. So it's acting outside of the system on the box. So this would be an external force. So this would not be an isolated system. However, if I were then to place this box on a tabletop, so we have a tabletop here such that there's a normal force like this, and this normal force is equal to the weight of the box and the particles in it, then that would balance out our forces, and we would have the sum of the forces would be equal to 0. And so then, or the net force, we could write it as the net force is equal to 0. So then it would be isolated. So If it were in free fall, it would not be an isolated system. If it were resting on a table, such that the net force is equal to 0, it would be an isolated system. Another example of an isolated system might be over here, this a bottle filled with some reacting agents here, some reaction mixture. This would be an isolated system as well. Any sort of reaction occurring in this bottle would be an internal force. And the system, of course, this needs to be resting on a table such that either that or in space, such that there are no external forces acting on it. The bottle would have no external forces, and it would be an isolated system. Now, it is quite possible that once the reaction occurs, that these particles start flying around all over the place, and the pressure builds up so much that they bust the glass. In which case, as soon as this glass were to bust out here, gravity would begin to act on it and it would pull it down. Actually, in reality, gravity is acting on each of these particles individually and pulling them down. So in the strictest sense, even these particles are not in an isolated system, but the force of gravity is so small that we can consider it to be an isolated system. Same is true in this case. Gravity would actually be pulling down on these little individual molecules, but that gravitational force is so small, we'll consider it to be isolated. Okay, so isolated system just has no net force acting on it. So the next thing I want to talk about, so we've covered systems and isolated systems. I would like to talk about total momentum of a system. So let's say that I have here two objects. Here's object A, so it has mass A, and here's object B, it has mass B. And let's say that, I don't know, actually let's give them some masses. Let's say this is 3 kilograms, and let's say this is 5 kilograms, and let's say this one has a velocity of 2 meters per second to the left. I'm going to be talking about momentum here, so I'm going to need to define a coordinate system. I'll stick with the traditional coordinate system here, and let's say the velocity of A is to the right at, I don't know, 1 meter per second. Then the total momentum of the system is simply the vector sum of the momentums of the individual pieces. So we have here total momentum of this system is equal to the momentum of object A plus the momentum of object B. Plus, if I had more objects, then I would just sum them as well. Okay, and these are vectors, so we have to be careful with our direction as well. So what is the total momentum of the system? Well, we have the total momentum would be equal to the momentum of A is 3 kilograms times 1 meter per second, plus the momentum of object B is 5 kilograms at negative 2 meters per second, because it's off to the left. And so when I sum these together, I have here 3 minus 10, I have negative 7 kilogram meters per second would be my total momentum of the system here. So the total momentum is simply the vector sum of all the individual momentums of the pieces. Okay. We could actually think here, to come back to this really quick, since an isolated system is one in which there is no net force acting on the system, and we know that a net force, or the sum of the forces, are equal to the mass times the acceleration. Now, if there's no mass, there's no sense in talking about a system. So the only thing that could be 0 is if the sum of the forces are 0, this means that the acceleration is 0. So we have an isolated system anytime the entire system as a whole has 0 acceleration. So no net force, no acceleration. In other words, it is in equilibrium. So that's momentum of a system and what a system is. So in my previous example, I showed momentum of a system only acting in the x direction, but let's extend this just a little bit and say we have something going off in two directions. So there's mass A, and here's velocity A acting off at some angle alpha, and here's mass B acting off at with some velocity b at some angle beta. Then the total momentum of the system, we can break the total momentum into x and y components as well. So the total momentum in the x direction would be the momentum of A in the x direction plus the momentum of B in the x direction, plus, if we had other particles there. And the same thing is true for the total momentum in the y direction. This would be the total or the momentum of A in the y direction plus the momentum of B in the y direction, plus however many other particles I have there. So we would see here that the total momentum of the system in the x direction would be equal to MA VA cosine alpha plus MB VB cosine of, really we have to say here, 180 minus beta, or we can use reference angles and make this a negative instead. So minus MB VB cosine beta. So that's up to you how you want to do it. And the total momentum in the y direction, very similar. We have P total in the y direction would be equal to MA VA sine alpha plus, because it's in the second quadrant, MB VB sine of beta. So we can have total momentum in the x and y directions just the same exact way as we had momentum in the x and y directions.